All right. Good afternoon, everybody. Today is February 11th, 2025, and this is SEVA VentRounds. And today we'll use a case that actually Ariel Garnero sent a while ago, but as I was preparing, I found that I thought that this was great. It's a case of one patient, 2 loads, and 1 PMUS. The disclosure is there's no endorsement of any mode, ventilator, or manufacturer. Whatever we say, it's our opinion. It does not represent the Cleveland Clinics. Your hosts are myself, Eduardo, mireles-cabodevila, and Rob Chatburn, and there are conflicts of interest. In general, this is a recorded session, so just keep your microphone muted. We may call upon members of the audience to comment, or you can unmute yourself if you want to make a comment, or use the chat function of WebEx. Just keep it muted if you're not going to make a comment, please. There are CMEs and CRCs that are offered from this activity. And just remember to complete your evaluation, and this is open for everybody. So what we have here is a key knowledge. Let me move this to the side there. That anybody that is managing mechanical ventilation needs to have clear. And we're seeing here the equation of motion. And in this example, we're going to be talking in specific about volume control with a square waveform for the flow. So meaning that the flow is constant through the inspiratory time. And just to highlight some of the key components, what you have here on this graph is the equation of motion, and this is a passive patient, so there's no PMUS, and you're going to have the P vent, and then you're going to have the elastic component or elastic load, which is elastance times volume. And you can see we like this graph because it demonstrates essentially how the elastic component, so the elastance times the volume, changes as the breath goes through. At the beginning, there is no elastic load, and at the end of the breath, when all the volume has been delivered, there is the maximum elastic load at that period of time. And then you have the resistive load, which is resistance times flow, and you can see that it's a constant, so it starts abruptly because it's a constant flow, so it rapidly rises, and it continues to be. So the resistive load is constant throughout the breath. And so if we put on top of the elastic load the resistive load, or you could put it below as you wish, the first step up is resistance, and then at the end the peak pressure is a manifestation of both the resistance and the elastic load. And so when you come to this graph over here, and you see P vent plus PMUS, the elastic load plus the resistive load, if we increase the resistive load, what you're going to see is an increase on this step up. So on the step up that occurs here, on the pressure that that is required to overcome the resistive load. If your load is elastic, go ahead, Rob.
If you're using your cursor or a marker, I don't see it.
Oh, I'm not writing on the screen?
Nope. Okay, well, yeah. All right, see, the little red lines, is that what you're talking about? All right.
Yes.
Yeah, it's very hard to see. It's very small.
Oh, okay. I'll put a laser pointer. How about that? Can you see it now?
There you go. That's better.
All right. Thank you, Rob. So the first step up that I was painting here is the resistive load. And if you were to do an end inspiratory hold, you would see that step up too there. Now, if it's an elastic load, remember it's volume times elastance, what you're going to see is an increase on the slope, because for each change in volume, for a constant flow, there's going to be more change in pressure. So as the elastic load increases, you're going to see that slope increase. And then if there is evidence of PMUS, then what you would have is the pressure waveform, whichever you wanted, even if it's the elastic or the resistive or the elastic, or I mean, whatever the load is, you're going to see a deformation. So you are not going to be able to read the load. Okay, Rob, any comments there?
Just to say that as PMUS goes up, then P-vent has got to go down if the right-hand side of the equation is constant. So that's why the waveform gets deformed that way in volume control.
I love that. So and you're highlighting the concept of work shifting, right? So if for the total work of breathing, if the PMUS is active, it's going to take away some of the P-vent required to overcome the elastic and resistive load, correct?
That's a good way to say it.
All right, wonderful. So now I have 3 waveforms, and these are, again, from Ariel Garnero, and we're going to get started with these images. So let's start with the tag, and we're only going to have to do this once because all of them are on the same mode. And so what's the tag? And this is a Hamilton ventilator, and this is the mode, the commercial name. You can use your app, or if you have used this ventilator, you can probably deduct it, or just by looking at the waveform. Sometimes it's hard because the flow in this ventilator is measured at the, and this, what you're seeing here is what is being measured at the Y. And so it doesn't look the perfect square waveform that you would expect to see. Anybody has any idea what mode? Rob, anybody has entered the mode so far?
No.
Let's see.
Nothing in the, oh, there we go.
All right, there you go.
CMVs, there we go.
Perfect. So this is volume control, CMVs. And so this is your classic, what we usually think it's volume control. So which means that we're controlling the flow, all right, the flow and the volume during the inspiration. All breaths are mandatory, and that in this case you can see, remember in this ventilator we'll put a little triangle if it's being triggered by the patient, or the ventilator interprets that as being triggered by the patient, and you don't see any of those. So that means that they're all triggered by the ventilator, and that would immediately make it a mandatory breath. But remember that the definition of a mandatory breath is a breath that it's either triggered or cycled by the machine, by the ventilator. And in this case, both are. And then S for set point, which stands for the targeting scheme. And essentially, we set all the values here. And you can see that we set the rate, the tidal volume, the PEEP, the oxygen, the inspiratory time, the flow rate, everything set by us. Rob, any comments on volume control?
No, except that on this particular ventilator, there's a wide range of flows that you can set for volume control, which is unusual. Yeah,
and that can really sabotage your existence. Absolutely. Yes. So as you and the other thing, besides having the ability to set different flow waveforms, it also, because it's measured at the Y, you're not seeing the classic waveform, which would be a square waveform over here. You at occasions, and you will see it, but that doesn't necessarily negate that this is volume control, because you're not seeing that beautiful geometric waveform. So if I ask you, by looking at this waveform, what is the load? What do you think the load is? All right, let's see some entries coming in. So let's start by the initial part. So this is a square waveform, and you obviously don't see a beautiful item here, a beautiful square waveform, but you see a step up here. But the key here is, because you cannot read very nicely, you don't see the initial step up here, and you see this all curved. You may be a little bit confused. Well, if you see there's a programmed and inspiratory pause, and that's why you see the pressure suddenly drops from here to here. And that's because there is a programmed and inspiratory pause. So the difference between the peak inspiratory flow, the difference between the end inspiratory flow and the plateau pressure, that's your resistive load. And it should be the same height as the initial step up. That's what we would expect, that this would be the same height as this one. So that's a key that tells you, oh, this looks like a resistive load. But then if you look at the expiratory waveform, the expiratory waveform takes an amount of time, actually it never reaches baseline. And the peak expiratory flow is blunted. You actually don't see any peak expiratory flow there. And those are markers that suggest us a prolonged time constant. And so I would say that based on this step up or step down that you see here, and the prolonged time constant, that this is consistent with a resistive load. Roberto?
Yeah, you want to draw in the elastic load since we can see that too?
Yes, so the elastic load essentially on this case would be this thing here.
Yeah, so it's the plateau pressure minus the PEEP is the elastic load, yeah. So the height of the plateau pressure, that distance there is generally larger than the distance between the peak and the plat.
Yes. So this will become relevant in a second, but you can see that there is a very high peak pressure, very high peak pressure. Why is the flow not zero at the pause? Well, because it's a manifestation of the plateau. Why it doesn't look? I'm gonna tell you in a second. So the question that Rana has is, ideally, these waveforms should look like this. This is how it should look, Rana. That's what you're looking for. But you're confused because you see this little loop or this decay here and this over here. Now, I'm withholding information, and it's not lack of love, but it's so that you can read these waveforms. But what you, just to highlight right now, the first thing is we have features of increased resistance, and then we recognize that the waveforms are not perfect, and we cannot see what we usually would want to see. This patient at this moment in time was undergoing a procedure, and obviously, whenever you see high resistance, thoughts will come through your mind. Well, is this bronchospasm? Is this the patient is biting on the tube? Is there secretions obstructing the tube? And in this case, it was something a little bit different. The patient was undergoing an emergent bronchoscopy. So it was intubated and went on to have a bronchoscopy. And this image that you see here with high resistance is while the bronchoscope is inserted through the ventilator. And I would just highlight for all of you is you can rapidly recognize that the peak pressure is 77, but the plateau pressure is all the way down here. And so we don't know how much it is because it was not measured, but we can certainly see that it's all the way down. Rob?
Yeah, good question. This is an unusual case.
Yeah. So then the bronchoscopy is finished, all right? And now you have this image. So I'm for the sake of time, I'm going to give you the tag because we reviewed it a second ago, VC-CMVs. And now you can see these waveforms again. And what is the load? I would ask the team. Now rapidly, I can see your brains are starting to recognize immediately the load. This is an elastic load, and this is again a patient in which there is no PMUS, there is no triggering anywhere. And if we remember our waveform, so you will see that this is volume control with a square waveform. And now, Rana, you can clearly see that the pause is right there, right? It looks like a pretty one. It's not as perfect because remember, this is being measured at the airway opening. But you can see as the flow increases rapidly, there is this step up. And I'm going to amplify it for a second. And you know that every time I amplify this, I make a mistake, but just tolerate it for a second. And so you can see now the step up in pressure with the increasing flow immediately. And I will point out that exactly at that moment in time, there's no volume being delivered, minimal amount of volume. And so if I come exactly up, I'm keeping the hand there, you see the flow go up and you see the pressure up. So in this case, this is all resistive load. This step up is resistive load. And the slope is the elastic load. And now you can see that because there's an end inspiratory pause, you can see that that same step up, now it's a step down, and then you have a beautiful plateau. All right. So it becomes much more evident. I'm going to return it to its size. Rob, comments?
Yeah, I'm just thinking about why the flow waveform was distorted before, but it's not now. And in other words, why did the high resistance of the bronchoscope cause a distortion in the flow waveform? And
yeah,
two things I could think of. One, I suppose conceivably this could have been running on its compressor, right? Not on the wall air. So in other words, any ventilator that has a blower will get a slightly distorted flow waveform with a very high load. But the other effect may be simply that for the first few milliseconds of inspiration, you were just filling up the patient circuit because the airway pressure was so high, and then once you filled it up enough, then it started giving you the flow that it was set. So that's kind of a tricky interpretation, right?
No, yeah, but I think that you're right on with that thought, Rob, because having a bronchoscope through the ET tube increases the resistance incredibly, and so the amount of pressure required to overcome that resistive load, the resistance is very high, and the compliance of the circuit starts playing into it.
Yeah,
I'm with you with that, and you can see that as a good high quality respiratory therapist, he did a pause because we should always do an end inspiratory pause. And now you have your plateau, and you can see that the plateau on this patient is 30. And so right where the cursor is now, you could argue with me that we should be measuring the plateau pressure at X amount of distance. And this is an area of controversy of where should you be measuring. But for the sake of this example, I'm just going to say that the plateau pressure is 30, which is certainly less than 77 for the same tidal volume. So I go back to the prior one, it's 310. And you can see that this patient indeed had an elastic load, but on the actual resistive load, because we put a bronchoscope, was much, much higher. And so this patient plateau was 30, which I'm not saying that it's safe, but it's certainly lower than 77. So a plateau pause should always be done because that's how you know what the lung is seeing. Rob?
I want to get back to this question about why there was not zero flow during the pause when the scope was in there. When you put in this situation, would you expect that there would be a leak around the scope?
Yep.
So then probably what was happening is that the flow didn't go to zero because all that pressure, it compressed a lot of volume in the patient circuit. So even though the ventilator flow control valve was off, all that volume charged in the circuit was discharging through the leak. And it was going through the flow sensor, right?
There was some leak. I could see some leak over here.
Yeah.
It's not major, but I cannot quantify it. So it's 293 on that simple measurement. So it's only 18 or 17. All right. So then, and this patient is again passive. So I'm not going to go into the PV discordance. And then, again, this is the last of the images. There's more here, but I thought that this would be a good one for us. And what you have, again, the mode is VC-CMVs. And so now the question is, what is the load? And or what's happening? This is not necessarily a load, but it's the same patient. Yeah, excellent. So now you can see from a passive waveform, you see how you were requiring a peak pressure of 35 with a plateau of 30. And now the peak pressure has gone down to 23. You can see that depression on the curve, instead of being a straight line, you see that scooping that is occurring over here. And I'm going to make it big just for the viewing pleasure of the team. So you see this scoop. You see the pressure, how it scoops even lower. Here it's even lower. And then when I go to this one, you actually, although the cut point is right here, you can see that at the beginning of the breath, the patient is not getting any or minimal amount of support. So that's one part. So remember, during inspiration, we in volume control, we don't look at the flow waveform, we look at the pressure waveform, and that's what we're seeing. We're seeing the deformations from the PMUS. And now you can see that little triangle that tells you that this patient has, that these breaths are patient triggered. So you all recognized PMUS. So now I want to go to what's the discordance, and I'm gonna number the breaths. There's this breath 1, breath 2, and breath 3. And so in breath 1, what's the trigger issue? Is it normal, early, late, false, or failed? I saw one pop up.
Yeah, there's another.
Yeah, so I think you guys are getting so good at this. It's really impressive. So for breath 1, it's definitely an early trigger. So it's not triggered by the ventilator. It goes triggered by the ventilator, and you know that because the ventilator is the holder of truth. And it's saying, I'm sorry, this is not triggered by the patient. This was triggered by myself. And you can see the evidence of PMUS. And not only you see PMUS during inspiration, you actually see it during expiration. But we'll talk about that. So definitely early trigger. What about breath 2 and 3? Yeah, 2 and 3 are essentially normal breaths. You can see that it's triggered, and I'm gonna just amplify for the sake of our viewing pleasure. And you could argue, if you take a look at them, is you see the drop in pressure here, and you can see that the flow actually started crossing even before. On this one, it happens relatively fast. And there's multiple reasons for this type of behavior, but you certainly see evidence of PMUS here and all the way PMUS over here. So let's talk a little bit more about that. I saw that Michael commented, I always do the same, about the possibility of a failed trigger. And so meaning that these breaths over here, these little, these items that we're seeing, that's the image that you would see on somebody that has a failed trigger. But it's happening very close to inspiration, so in the early phase of expiration. And there's evidence of PMUS during inspiration. And so that makes you think that this is likely early and normal. The other breaths are normal. And we did do an end inspiratory pause, which now I realize that I should have put there. But what it did show was a long inspiratory effort. So confirming this part. But alrighty. So in terms of inspiration, oh, Rob, sorry, any comments on trigger before we go to inspiration?
Yeah, because the comment is that there might be some evidence between 3 and 4 that the flow crossed 0, but then went back down again. If you zoom in, I think maybe you could see that, but it's hard to.
Yeah, I did see it, and that's why now I feel guilty of not putting the pause that Ariel did, because the pause clarified everything.
Yeah.
But that again, as in our last session, the key here is if you don't do an end expiratory pause, it can give you clues to know exactly what's going on. So during inspiration, is this assistance over assistance or under assistance? This is a tricky one. And I would. Yeah, this is a tricky one. So we have said that in general, there is assistance if the pressure has stayed above the baseline, which is happening actually on all the breaths. It has not gone below. You could argue that all these breaths that and I'm sorry for not having put the pause, but essentially the effort starts here and it goes all the way over here. Those are the breaths. So a big part of the breath from here to here is not getting assisted. And the problem that we have right now is that this is not very well defined how to do it at bedside. And I would say that if you say this is under assistance because of an inappropriately used mode, you could be correct because we're not supporting at all. And the patient is trying to do an effort and it's not getting any support, albeit the pressure is above the baseline. So assistance would be the right answer in a test, and just highlighting one of the inconsistencies in what the knowledge level that we have right now. Rob?
And that's exactly right. This is an area we need to do a little bit more work in defining the metrics, right?
So great job. And then in terms of cycle, for breath 1, we're not going to read breath 1 because we know that's an early trigger. And so that gets just the name of early trigger. That's it. But for breath 2 and 3, is this normal, early, or late? And I kind of gave you the answer already, but I want you to reinforce it in your brain of what is this, early or late?
There we go.
Yeah, excellent job. So this is consistent. So for breath 2 and 3, this is early cycle. So the machine cycled earlier in reference to the patient. Cycled earlier in reference to the patient. Now, I just want to remind you that for breath 1, this is not an early cycle. This is a manifestation of the early trigger. And that's because if you try to, the importance here is that if you treat the reverse trigger, the early cycle will be taken care of. And so early trigger can cause early cycle, but the problem is the early trigger, not the early cycle. And then during exhalation, there could be, this seems to be perhaps some amount of work breathing, but we didn't see that on the pause. So I'm gonna call it normal, but it's pretty annoying. It's not a nice curve. There's a lot of activity, perhaps some inspiratory effort, although we didn't see that on the pause. So in summary, Rob, before I go into the summary, comments?
Yeah, just to reiterate what you said, I imagine you would have seen early triggers and early cycles mixed together. And someone might say, well, which one do I pick, right? So, and I think you already said the way to determine what's going on is to do the expiratory hold and that would unveil the very long PMUS.
Yes.
Which would indicate, the problem is the early cycle, primarily.
So this patient, just for the sake of what was changed to pressure support, the goal was eventually comfort. You can see that the oxygen levels are going down. The patient got a procedure done, improved, and eventually got weaned off pressure support. So I would say today you have reviewed the full equation of motion in one single case. And I love when one case can show everything. So you saw the resistive load. And when you saw the resistive load, you recognized on volume control with continuous flow that the initial step up was due to the resistance. And then if there's a plateau pause, the drop is part of the resistive load. So these are manifestations of resistance. The elastic load we saw later on is manifested by the slope on the pressure curve. So the steeper the curve is, the higher the elastance is. So meaning the lower the compliance. And if you do a plateau pause, that will be manifested and measured during the plateau pause. That's the manifestation of your elastic. And then we saw the PMUS and how the PMUS actually deforms your waveform down when there's presence of PMUS in the waveform. And when that's present, you cannot really see the elastic or resistive load. It models it and it makes it disappear. Sometimes you can see through if it's a short effort, but when it's present, it's hard for you to see. And sometimes the only way to see it is to see elsewhere or wait until a passive breath will occur. So I think that if I would ask, if they ask me what is something that you would say that it's key for you to master, is to master how does a passive waveform looks for volume control and for pressure control and with the different waveforms. When you have that in your mind, then you will be able to see the resistive, the elastic, and the PMUS component, because you will be able to recognize abnormal from normal. Rob, any other take-home messages for the family?
No, I think that's a great summary.
Excellent. So here's the CME for the CCF caregivers. Again, go for it. And the CRCs for our RTs. We have a new thing. I will invite you again. Now we have opened the SEVA course to everybody, and you can register on this link, and that will take you to an explanation of everything that's available. But I just will put this slide here that will highlight that you can get online access only. And if you want to do any of our in-person courses, you can go from, you always have to start with the fundamental, but after that you can skip and do advanced or master, depending on what you need to do. And so with that, we thank you for all your time and engagement today and hope you have a great day. Thank you.